Let us start with reading 7 of study session 2, Statistical Concepts and Market Returns. In this LOS, we are going to understand the difference between descriptive statistics and inferential statistics, population and sample, and different types of measurement scales. We will also define parameters, sample statistic, population parameter, and frequency distribution. Then we will look at the relative frequency and cumulative relative frequencies given a frequency distribution. We will describe the properties of a data set presented as a histogram or a frequency polygon. We will define, calculate, and interpret the measure of central tendency, for example mean, median, etc. We will look at the quartiles, quintiles, deciles, and percentiles. All of them are from frequency distribution. We will look at the range and mean absolute deviation. Then we will look at the range, mean absolute deviation, standard deviation, etc. of population and sample, which are the measures of variation of data. We will look at Chebyshev inequality and its interpretation. We will look at coefficient of variation and Sharpe's ratio. We will also look at certain higher order movements such as skewness and kurtosis. And finally, the use of arithmetic and geometric mean while looking at investment returns. So let us start with the nature of statistics. There are two major ways in which we can study statistics. One could be descriptive, another is inferential. And in order to understand them, we have two basic concepts, which are population and sample. The population covers all the elements of the group. When we have information about all the elements of the data set, we call it a population. And sample is a subset of population. It could be selected randomly or based on certain procedure. So this is the subset which tries to represent the population. So the descriptive statistics talk about the features of large data sets and their summarization. Suppose we have a huge population, we have different values. If we want to calculate, say, average of all the numbers, then it will be called descriptive statistics, since it is summarizing all the values of the population. So population is important in descriptive statistics, whereas in inferential statistics we just take a small sample and based on the values of the sample itself we try to infer what should be the nature of the whole population. This kind of statistics is called inferential statistics. This is based on estimates. We need to have sample statistic from which we try to estimate the features of the population. So it uses small set of data from large data to make forecast, adjustments, or estimates. This is the broad difference between these two branches of statistics. Now let us move to the next slide. Here we discuss four major types of scales for measurement. First of all, we have nominal data. So in this kind of data, we can have numbers or alphabets or some kind of codes which need not have any value in terms of comparison. For example, if we have two PAN numbers, we do not compare them in terms of which is more or less. Each of them are nominal. They are just as names. Or for example, for the same class we have section A, section B, section C. So these are just the names of the sections. So this is nominal data. They do not carry any other information. The second type of scale is ordinal scale or ordinal data. In that we have rankings. For example, B school ranks. Say B school A has first rank, B school B has second, C has third, D has fourth, and so on. So we can compare here that A is better than B, B is better than C, C is better than D. But again, this kind of scale is also having a limitation that we do not know by what amount A is better than B and by what amount B is better than C. We only know the rankings, but we do not know the difference between these two. It is possible that A is slightly better than B and C is way better than D. But this ranking does not tell us that. That is a limitation of ordinal data. Now let us look at the interval or scale data. For example, the ratings. We take the same case. If we have the ratings, we have the scores of say these B schools or some mutual funds or some companies where we have interval or scale data. A better idea of comparison, we can take the difference to compare. So this is interval scale, and the last one is the ratio data, where even the ratios make sense. In the case of interval data, ratios don't make sense. For example, we cannot say C is 4 times better than D just because the score 5.2 is 4 times the score of D, which is 1.3. So we cannot say C is 4 times better because the ratios do not make any sense in interval data. For that we need to have ratio data. For example, when we talk about money or price, dollars or rupees, they can be compared in terms of ratio. For example, the $100, $50, they can be compared. $100 is twice as much as $50. So there we can have ratios. So this is the best scale among these four. It has the maximum information associated with that. Now it depends on the purpose, which of these scales is to be used. The more quantitative data we have, we'll use the fourth scale, that is ratio scale. For qualitative data, we use nominal scale. Or for our other purposes, we can choose even ordinal or interval data. Let us move to the next slide. These are the basic statistical terms we need to understand before we move forward. Firstly, the parameter. Parameter is in context of a population. It is a measure that describes the characteristic of a population. So whenever we call parameter, we mean population parameter. For example, if we have say 1000 students as a whole population, then the average age of all 1000 students, this is a population parameter since we are talking about the whole population. This average will describe the characteristic of 1000 students, the complete population. So this is a population parameter. At the same time, when we talk about sample statistic, this describes the characteristic of a sample. Sample is drawn from the population, which is subset of the population. For example, these 1000 students were the population. If we draw a small random sample of say 50 students, out of these 1000 and we take average of these 50 randomly selected students, this is the characteristic of the sample. So this average is actually the sample statistic. Although we'll see how the sample statistic can be used to estimate the population characteristic. That is, with the help of this sample statistic, which is the average of these 50 students, we can estimate the average of these 1000 students. That is precisely the objective of inferential statistics. We will see that example later. A frequency distribution is a table that summarizes a large data by assigning the observations to intervals. So frequency distribution is, we look at the data, divide it in terms of intervals and see within that intervals how many numbers of data points are fitting into. We'll look at an example to clarify this further. The relative frequency distribution is basically as a percentage of total outcomes, the same as frequency distribution, only as a percentage of total, so that it becomes relative. And cumulative frequency distribution shows the percentage of observations which are less than the upper bound of each interval. For example, if we have say 5 ages, say somebody is 10-year-old, other person is 12, 13, 14, 19, 26, 27, 35. Suppose these are the values, 8 values. So in order to understand them better, we just convert them into frequency distribution, where we divide the intervals like 10 to 15, 15 to 20, 20 to 25, 25 to 30, 30 to 35, and so on. So among 10 to 15 we have 1, 2, 3, 4 values. Between 15 to 20 we have only one value. Between 20 to 25 we have no value. Between 25 and 30 we have 2 values, and 30 to 35 we have 1 value. So this becomes our frequency distribution. So these are the absolute numbers. If we want to calculate the relative frequency distribution, we just add this. So there are total 8 values. So if we look in terms of percentages, 4 by 8 is 50%. So this is relative frequency. So 50% of the values lie between 10 and 15. Similarly, 1 by 8 is 12.5%. So these number of values lie in this interval. This is 0%, this is 25%, this is again 12.5%. Summation of these percentages will be 100% total. So this reflects the relative frequency distribution. So now the cumulative frequency distribution says the values less than upper bound. In this case, upper bound of the interval is 15. So less than 15 will be 50%. Less than 20 will be 62.5%. Less than 25 will be again 62.5%. Less than 30 will be 87.5%, and so on. So these numbers are cumulative. They are sum of the previous values. 50, 50 plus 12.5, 62.5 plus 0, 62.5 plus 25, 87.5. This is how we are calculating. We will take one more example to clarify this further. Say these are the values, data, given to construct a frequency distribution table. So we need to calculate absolute, relative and cumulative frequencies. Okay. So let us divide that into intervals. We have divided 10 to 20, 20 to 30 and up to 60 to 70. Then we'll count to find out absolute frequency. So how many data points are between 10 and 20? So the convention here is we include first one, but we do not include the second one. That is, x should be greater or equal to 10 but less than 20. That is the convention of the interval. So 10 is 1, this is another, this is another. 10, 11, 12. There are 3 values between 10 and 20. Between 20 and 30, if we see 1, 2, 3, 4, 5. There are 5 values between 20 and 30. Similarly, between 30 and 40, 1, 2. There are only 2 values. Similarly, we can find out other values. The total comes to 20. There are totally 20 values. If we look at relative frequency, we need to divide this number by 20 so that we get the percentages. So we can say 15% of the values lie within this interval. 25% of the values lie between 20 and 30, this interval. Now let us look at the cumulative frequency. We can calculate them in terms of percentages or absolute frequency. Usually we take absolute frequency. So 3 says these are the number of values which are less than upper bound of the interval, which is 20. So if we say how many values are less than 30, which is the upper bound of the second interval. So we have this 5 and even this is less than 30. So we take sum of these two. 5 plus 3 is 8. This is 5 plus 3. Similarly, if we say how many values are below 40, which is the upper bound of this interval, we know that these two values between 30 and 40, and there are 8 values which are less than 30. So 8 plus 2. This 8 plus 2 becomes 10. There are 10 values which are below 40. Similarly, you add this 10 to this 3, you get 13, and finally you get 20, which is your cumulative frequency of last interval. Since all the values are less than 70, so these should be 20. All 20 values are less than upper bound of the final interval, which is 70. So this is how we draw a frequency distribution table. Later we see how we do graphs from these tables. Let us look at the histogram. This is one of the basic frequency charts. We have these intervals here. We have divided, for example, this is the return of some stock over the period of last 10 years. So these are the intervals 0 to 10%, 10 to 20, 20 to 30, and so on. On the negative side, we have minus 10 to 0, minus 20 to minus 10, minus 30 to minus 20. And if we look at the data, out of those years, in 1 year, the return was between minus 30 to minus 20. In 2 years, the return was between minus 20 and minus 10. In 3 years, the return was between minus 10 and 0%. And in 7 years, the return was between 0 to 10%. So the histogram gives us a good idea what should be the expectation from the stock in future, or at least how it has been performing in last 10 years or so. Similarly, we have other charts such as frequency polygon. In this, instead of bars, we just have points, and we just add these points. These are the midpoints of the interval. We have, for example, minus 30 to minus 20. So midpoint is minus 25, where we are plotting this. Say this is minus 20, this is minus 10. So midpoint is minus 15. So we have these midpoints where we look at the frequencies. Now let us move to the next slide. We talk about measures of central tendency. So we would like to know what are the values around which the data is centered. So the most popular measure of central tendency is the mean. Though mean could be arithmetic mean, geometric mean, or harmonic mean, but generally when we say mean, it refers to arithmetic mean only. So first measure is population mean, that is arithmetic mean value of the population. So the formula is sigma xi divided by n, summation of all the values divided by number of observations in the population. We need to be careful that we are using the number of observations in the population itself, and the population mean is represented by mu. On the same lines, we can calculate arithmetic mean for the sample, where small n is the number of observations in the sample and x bar is the sample mean. So we are using only sample values. Their summation is divided by number of observations of the sample. So this is our sample mean. Finally, we have weighted mean. When we have disproportionate influence of different values, we assign these weights, multiply the corresponding values with their weights, and then add them up. Finally, we get weighted mean. Now let us look at the other measures of central tendency, such as median. Median is the mid value of data set when it is arranged in ascending or descending order. For example, if we have ages of students such as 10, 11, 14, 19, 27 and 30 and 31. So if we see, these are arranged in a ascending order. So the mid value will be, these are total 7 values, 1, 2, 3, 4, 5, 6, 7. The mid value will be 4th. So 19 is the median. See, the calculation is very simple here because we are not actually using the values. We are just putting them in a sequence and using the mid term. So these values, however high or low they are not actually influencing the median. So if the number of observation are odd, then the term which is the median term is n plus 1 by 2. In this case 7 plus 1 by 2, which is 4. So 4th term is the median. In case we have even number, for example 31 is not there, so it is just 10, 11, 14, 19, 27 and 30. 31 is not there, there are just 6 terms. In that case we take the average of middle 2 terms, that is 6 by 2, which is 3, and 6 plus 2 by 2, which is 4. So 3rd and 4th term, 14 and 19, we will take the average of these two. Then we have mode. Mode is the value which occurs maximum number of times, most frequently occurring value. Example, we take the same age example. Suppose there are students with these kind of age data, 1, 2, 3, 4, 5, 6, 7. We have 8 data points. So 13 should be the mode because 1, 2, 3. 3 students have the age as 13. So maximum frequency is of 13. So that should be the mode of this data. The data could be multimodal. For example, unimodal, bimodal or trimodal, depends on the number of modes it have. For example, if instead of 8 data points, if we have 9 data points and there's one more value 10, then we have 2 modes, 10 and 13, and we can have 3 modes or any number of modes in the data. Let us look at the geometric mean now. This is the nth root of product of n terms. The basic definition of geometric mean, but when we use it for returns, we use 1 plus the return rate for all the terms. For example, if the return is 5% in first year, 6% in second year and 7% in third year, then geometric mean of return is not going to be 5 into 6 into 7 and cube root. This is wrong. The right way of doing it is cube root of 1.07 into 1.06 into 1.07, and for rate we subtract 1 in the end. So this is going to be our geometric mean for returns. Let us move to the next slide. Now we have harmonic mean. This is mostly used for averaging the ratios. This is the least common among the 3. So this is reverse of the average of the reverse values. I'll take an example. Suppose there are three values 3, 4 and 5. If I want to take harmonic mean of these three, I add 1 by 3, 1 by 4 and 1 by 5, reverse of them. Okay, then I divide it by 3 since I want to take the average, and finally I'll reverse it. Okay, so this will become harmonic mean, or this 1 by 3 can be written as 3 here. Instead of 1 by 3 in the denominator, we can write 3 in the numerator, that is n here. So what is the practical use of harmonic mean? I'll give one more example so that the relevance of harmonic mean and its usage will be clear. Let us say a car moves from point A to point B with the speed of 30 km per hour, and it returns from B to A at the speed of 60 km per hour, and we want to know what is the average speed in the whole journey from A to B and again B to A. So this average cannot be given by arithmetic mean. If we use arithmetic mean, which is 30 plus 60 divided by 2, that is 45 km per hour, that will be a wrong answer. In this case, harmonic mean should be used. That is n, which is 2 divided by 1 by 30 plus 1 by 60. So it will be 40 km per hour, which is the right answer. We can just verify it. We know the average speed is total distance divided by total time taken. In this case, say the distance from A to B is x kilometer. So the total distance is 2x kilometer. Okay. And the time taken while going from A to B is going to be the distance divided by speed, x by 30. While coming back, the time is x divided by 60. X was the distance, 60 was the speed. So if we remove x, the value is same, the harmonic mean, which comes to be 40 km per hour. So in such cases, we use harmonic mean instead of arithmetic mean. Now let us move to the next slide. There are certain other measures of location that says the value at or below which the stated fraction lies of the data set. For example, 25% of the values lie below certain number. So we need to find what is that number, or say 10% of the values, or instead of percentage we can have quartiles. So there are 4 quartiles. Quintiles, that is 1 by 20th, that is 1 quintile. So there are total 20 quintiles. Then there are deciles, 1 by 10, a percentile is 1 by 100. The formula becomes n plus 1 into y by 100. Let me explain it with an example. So this is the value, this is the data set. There are total 11 values. We have to calculate 3rd quartile, 6th decile and 80th percentile. Let us start with 3rd quartile, the first case. So there are 4 quartiles. We know 0 to 25%, that is 1. Then 25% to 50%, that is 2nd quartile. 50% to 75% is 3rd quartile, and 75 to 100% is 4th quartile. Okay. So if this is the complete data 0 to 100%, we need to find out 3rd quartile. So this is 1st, 2nd, 3rd. So this is 75%. So what is this number here below which 3/4 of the total values lie? For that we calculate using the formula which we have just seen, n plus 1 into y by 100. In this case, since we are talking about third quartile, which is 75 by 100, we know it. From there we use, and the value which we get is 9. So ninth term should be the value, provided it is in the correct ascending order. We have already arranged it in that sequence. So if we look at the ninth term, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 19%. So that is our value. 19% is the value, which is third quartile. So we can say that 75% of the value lie below 19%. Now let us look at the second part of the question, which says what is the sixth decile value. So if there are 10 deciles, similarly we can say 10 deciles will be 0 to 10%, 10% to 20%, 20% to 30%, and so on. There will be 10 deciles. We need to know the value of sixth decile. Same formula is used, 11 plus 1 into 6 by 10. Sixth decile is 6 by 10. So we need to have the value of not 7.2% but 7.2th term. But there is a problem, since we know that there is only 7th term and there is only 8th term. We don't know what is 7.2th term. We need to calculate the value which corresponds to this term. So we have 70%, we have 18%. We need to find out what is between them. Okay, that too 20% between them. So we use the values. 17% is the first value. 7.2 is the term which we want to calculate. 7 is the previous value of the term, and x8 and x7 are the numbers of 8th term and 7th term, 18% and 17%. So the answer becomes 17.2%. This is the value of sixth decile. We can say that 60% of the values fall below this data, 17.2%. Now let us come to the third part of the question, which asks 80th percentile value. So this is clearly asking what is the number below which 80% of the values lie. We are using the same formula, 80 by 100 represents 80th percentile. The value is 9.6. We know there is no 9.6th term here. There is only 9th term and 10th term. So we know it should be somewhere between them. We use the formula. This is the previous value, 9th term. This is the value of the term which we have calculated here. 9.6th term needs to be found out. This is the first term, 9th, and these are the values of 10th term and 9th term. The output is 19.6%. So this is the value which tells us that 80% of the values lie below 19.6%. So this is the significance of these other measures such as quartile, decile, quintile, etc. So far we have talked about measures of central tendency and the measures of location. Now let us move to another aspect, which is measures of dispersion. So measures of dispersion try to capture the characteristic of the data which shows how much variation is there in the data. For example, the simplest measure of dispersion is range. So if we know the maximum value and the minimum value, the difference between the two becomes the range. And that is one of the most commonly used measures of dispersion. For example, if there are 10 students and the age given are 10, 11, 11, 12, 13, 17 and so on, and the highest is say 21. So if they are in increasing order, we know if we have to calculate the range, it is 20 minus 10, which is 11. So we know the range is 11. So this is how much variation is there in the data. So the range becomes very popular and common way of measuring dispersion. For example, if we compare this data set 1 with some other data set, again there are say 10 students, but their ages are like this: 14, 14, 15, 15, 15, 16, 16 and up to 17. There are 10 students. We know minimum is 14, maximum is 17, the range is just 3. So we know there is very little variation in the data. The ages of these students are very close to each other. So measures of dispersion try to capture this. So the variation or dispersion is much less in dataset 2 as compared to dataset 1. This was about range. Let us move to next measure of dispersion, which is mean absolute deviation. Mean absolute deviation is the mean of the deviation of all values from the mean. Let me explain it once again. If there was a large population, from that we have drawn a sample of 5. So n equal to 5. The values are say 10, 11, 11, 12, 13, 13. So these are the say 6 values. Okay. So first we calculate what is the average of these 6 values. Which is x bar is 11.66, which is just summation divided by number of terms, which is 7. So this is coming from 70 divided by 6 is 11.66. Now we need to calculate the deviation, which is xi, these are the values of xi, minus x bar. So now the deviation. So xi minus x bar is minus 1.66 in this case, 0.66 in this case, again 0.66. Here 12 minus 11.66 is 0.33. In this case 1.33, again 1.33. This is the deviation. Now we need to know absolute deviation. Since we want to make sure that these positive values are not neutralized by negative values, we take the absolute value, xi minus x bar, absolute value. So mod of this value is 1.66, 0.66. We can see that these two values again were negative, but here it will be only positive, 1.33, 1.33, and we have to take the sigma, the summation of all these values, xi minus x bar, which is equal to 6, and the number of terms we have is 6, so we have to divide by 6. So this divided by 6 will become 1. So mean absolute deviation in this case is 1. That is how we calculate mean absolute deviation. Now the last is population variance. This is very important term, extensively used in risk. This is equal to the variation, the deviation from the mean, the square of it, and then we take the summation and divide by the number of observations. And if we have to calculate the standard deviation, sigma, this becomes the square root of population variance, which is summation of all the values square divided by n. Here we are talking about the population. In case we want to calculate for the sample, we take n minus 1 instead of n. Yes, this is the formula for sample variance. Instead of n, we are using n minus 1. The reason behind that is, Since we are estimating x bar, we do not know the mean of population, we are using the sample mean here. So we have already lost 1 degree of freedom in the calculation. Because of that, we are using n-1 so that we are not underestimating the variance. To avoid the underestimation of the variance, we are using n-1 in the case of sample. Now let us look at one of the most fundamental theorems which will help us to get the basic idea about any distribution. Chebyshev inequality. It states that for any distribution with finite variance, the proportion of observations within x standard deviation or k standard deviation of the arithmetic mean is at least 1 minus 1 upon k square, defined for all values k greater than 1. Let me explain it with the help of an example. If there is a population with say 1000 values and say the mean is 10, so we know there will be lot of values around 10. There will be very few values which are close to 1. There are very few values which are above say 20. So in general the distribution will be something similar to this. It could be normal distribution or it could be some variation of that, but in general it looks like this. So we want to say that around the mean, which is 10, if we move in this direction left or if we move to right, what percentage of values lie between k standard deviation? For example, if the mean in this case is 10 and standard deviation is say 2, value of one standard deviation is 2. Okay, so if we say one standard deviation around the mean, that says 8 to 12, that is 10 minus 2 to 10 plus 2. So if this is 8, this is 12, these values are one standard deviation left and one standard deviation right. Okay, so we say within one standard deviation, that means 8 to 12. When we say 2 standard deviation, that means 10 minus 2 into 2 to 10 plus 2 into 2, that is 6 to 14. This is the range of 2 standard deviation around the mean. So we need to know at least what percentage of values fall in this range. So that is where Chebyshev inequality helps us. If we want to know one standard deviation, let us put k is equal to 1. But we know that it is not defined for k equal to 1. So that part is not applicable. Let us take k is equal to 2. So it is 1 minus 1 upon 2 square, that is 3 by 4 or 75%. So we know for any distribution, we are not taking any assumption about the distribution whether it is normal or not normal. For any distribution, at least 75% of the values will fall within one standard deviation. Let us take k equal to 3 standard deviation. So we have 1 minus 1 upon 3 square. So we get 88.89%. So this is the percentage, 88.89%. At least these many values will fall within 3 standard deviation. At least 75% of the values within 2 standard deviation. Similarly, we can find out for 4 standard deviation. We call it 4 sigma, 5 sigma, 6 sigma. This is the concept used in quality management, where the number of defects fall to such a low number that we know that most of the products are of good quality and in this range. So that is the significance of Chebyshev inequality. When we have normal distribution, we can improve these numbers further. We'll have better idea about the distribution. Now let us look at the few other concepts. For example, coefficient of variation. Since we have already looked at the standard deviation, but this is an absolute number. As we have seen in the case of age, when we are looking at the value of range, similarly we can calculate the standard deviation also. Suppose there are two data sets. Data set 1 where there are ages of 10 students, and data set 2 the ages of another 10 students. Say standard deviation in first case is 10 years and in second case it is 2 years. If we know that we are comparing the ages of the students of the same class, we know that a comparison between standard deviation makes sense. But if this is students of say primary and these are the university students, and we want to compare the variation in the data, so in which data the variation is more, so we cannot know unless we know the mean also. So we need to have a ratio. We divide this number by the mean of these students, that is say x1 here and in this case x2. That will give us in terms of percentage what is the variation. For example, if the average age in this case is 15, so our standard deviation is 0.66. If the average age in this case is say 20, this is 0.1. So this gives us a better idea. These are the ratios which can be directly comparable where the variation is higher. So this is coefficient of variation. If we divide sigma by mean, we get coefficient of variation. S by x bar for the sample. Sharpe's ratio is the concept which is used in portfolio management to measure the performance of a portfolio or investment, where we want to know what is the return per unit of risk for an investment. As we already know that risk is measured in terms of standard deviation of the portfolio. So this is portfolio return over risk-free rate divided by standard deviation of the portfolio. So this basically gives us an idea. Return above risk-free per unit of risk. Let us move to the next topic. Here we discuss the properties of a normal distribution. This is one type of distribution which is commonly found in nature. Here the mean, median and even mode are equal. See, this is the point at which mean, median and mode, all three of them lie. This distribution is symmetric around the mean. This is completely described by mean and standard deviation. We do not need to know any other parameter. If we just know the mean and the standard deviation of a normal distribution, we know what is the characteristic of the population. We do not need to know any other parameter. As we discussed while we were talking about Chebyshev inequality, when we have the idea about the distribution that this is a normal distribution, the numbers will further improve. 68% of the observations will lie between 1 sigma, 95% observations lie between 2 sigma. In the case of Chebyshev inequality, we have seen that if we do not know the distribution, at 88.9% of the values will lie between 2 sigma. But if we know the distribution, we can say that even 95% of the values will lie between plus minus 2 sigma. So so our knowledge about the nature of the distribution helps us to predict the range better. Similarly, 99% of observation lie between plus minus 3 sigma if it is a normal distribution. There are higher order movements which are fixed, like skewness, which is third movement, which is 0, and fourth movement, which is 3. So for all normal distribution, these values are going to be 0 and 3, so we do not need to know them. They are fixed. As we know, the second movement is variance, third is skewness, fourth is kurtosis. That is why we just need to know these mean and standard deviation. Only two parameters are able to explain the normal distribution completely. Now let us look at these skewness and kurtosis a little further detail. Skewness basically refers to the extent the distribution is not symmetrical. For example, if the data is positively or right skewed, then the mean is going to be higher than the median and the mode. If there are more values on the right side, then it will be right skewed. For example, in this case, mean is higher than the median and median is higher than the mode. So the data is positively skewed. The more percentage lies on this side. And in the case of negatively skewed, the more values lie on the negative side. That makes our mode to be the highest and mean to be the lowest. So mean is the lowest, mode is the highest in case of negatively skewed data. So data is not basically symmetrical in these two cases. So these distributions are not normal, because we know in the case of normal distribution the value of skewness is 0 and mean, median, mode, all three values are equal. Now let us look at the kurtosis. The kurtosis measures the peak of the distribution. So there are three types of kurtosis: leptokurtic, platykurtic or mesokurtic. There could be three kinds of distribution. If the distribution is more peaked, then the kurtosis value is more than 3. If it is less peaked than the normal distribution, then it is less than 3. And we know for normal distribution it is 3. So the kurtosis is same as normal distribution, which is mesokurtic. So for example, this is the case of leptokurtic distribution. And if we have to draw platykurtic, is going to be like this. This is platykurtic. We can even calculate these values of sample skewness and sample kurtosis.